Hi everyone and welcome to our second episode of SOS, where today we're going to be having a look at motors and generators. So the first thing we really need to understand then is what actually happens when we have a current carrying wire placed into a magnetic field. And the answer is that those two things are actually going to interact. Because any time a current flows through a wire, it generates its own magnetic field. So then we've got two magnetic fields in the same place, and of course they will interact with each other. So because those two magnetic fields are going to push on each other, they end up creating a force on the wire. And that force is always at right angles to the magnetic field. Now, what we see happening actually depends on where the wire is and how it's structured. One of the things they could ask us about is a single piece of wire that's passing through a piece of paper, for example, and they'll ask you to then draw the actual magnetic field lines you would expect to see. So what we end up with is this. So the little X there represents our piece of wire, and then we actually get a circular, and please excuse my terrible drawing of circles, but circular field lines around it. Now, the other bit we need to add to that, which I haven't yet, is the arrows to show the direction in which those will move. Now, the key thing here is we're using our right hand, okay? Now, with your right hand, what you're going to do is you make a fist, and then from that, stick your thumb up, okay? So we have our thumbs up sign. Now, what we've actually got here is your thumb is going to be pointing the direction the current is flowing in, and then the way your fingers curl is actually going to show us the direction of that actual magnetic field. So you can see it curls around. So what we do is if it's going into the piece of paper, then we're going to have it going in this direction. Whereas if it's coming out of the paper, then it goes the other direction. So you should then be able to label your arrows on there. So the next bit we need to know about is this thing called Fleming's left-hand rule. Now, before you actually go into the exam for your first physics paper, the most important thing you can do is know the difference between your right hand and your left hand. If you don't know that, then I guarantee that this question is going to go badly for you. So Fleming's left-hand rule then actually, as the name suggests, uses your left hand. Now, what we've got to do here is we're going to set up this weird little sort of signal. Now, this is how we're going to remember what's happening in our question. The only time we're going to need to use this is in questions where we're looking at diagrams like that. So we've got our North Pole, our South Pole and our magnet, and we've got our current carrying piece of wire in the middle. Now, what we need to do is understand how that wire is actually going to move. Hence, this comes into play. So we've got three of our fingers involved here, okay? So your thumb is actually going to be the movement, so it's going to tell you whether the wire is going up or down, whatever it's doing. We've then got our first finger here, which is our field, okay? So it points from the north, the main body of your hand, to the south, the tip of your finger. And then our second finger, this one, is going from positive to negative. So that's our current. So thumb is the movement of the wire, your first finger is your field, north to south, and your second finger, the current, positive to negative. Now, the next thing is you need to work out how to actually angle your hand. So if we've got a system whereby it's actually coming, so this is our North Pole on the bit of paper, and there's the South Pole, then you align your hand like this. Then we need to have a look, is the current going into the paper or is it away? So we then need to arrange, is our hand pointing that way or is it that way? So have a look, and when it's pointing, remember it's three-dimensional, these pictures, and they're not actually 3D, they're just drawn to hopefully give you that impression. Then you've got to arrange your hands like this. So if the current's actually coming at you now, then what we'd have is north is here, south is here, and it's pointing this way for the current. Then what we're going to see, that bit of wire is going to move downwards. If it was the other way, then the wire moves upwards. The only thing that we've changed is the direction the current is flowing through the wire there. So practice this. Get it lined up. You might have to turn your hand that way or that way, this way. So you need to just sit and practice. You'll look a bit strange, but don't worry, it will therefore help you in the future. hopefully we've now got a basic understanding of how we're going to generate these different interactions between our current carrying wire and a magnetic field. So Fleming's left-hand rule is going to be really important as we move on here. Now what we're going to do is we need to understand how we can use these to actually create some rather simple devices. And the first one of these devices we're going to look at is a motor. Now when we're talking about a motor, we're talking about the very simple version, which is here. So we've got our north pole of the magnet and the south pole of the magnet, with obviously the field running between. And we've got a single coil of wire there. Now what we can see is, because we've got a coil of wire, what actually happens is the current is going to flow in on this side, and then as it comes back on the other side, the current is going in the opposite direction. So this is really important, and where Fleming's left-hand rule comes in. So what we actually need to do is, if we use Fleming's left-hand rule for this side of the piece of wire where the current is going in that direction, then we'll find it's actually going to be pushed downwards. Whereas on this side, where the current is coming in this direction, it's going to push it up. So we've actually got the two sides of the bit of wire, therefore, being pushed so it starts to twist. So that's what we see with our motor here. It's all down to the fact that when we've got it set up, one side is coming in and therefore moves in one direction, the other side is coming out and it moves in the opposite. So we're setting up something that's hopefully just going to turn. If it's a single coil of wire, then we're going to hit a point where it's actually just going to snag, so it doesn't work. What we need to include is this little thing here called a split ring commutator. It's through using this that we can actually have our coil spin continuously. Because what we've actually got here is a little device that you can see there's a gap running down the middle there. Now that gap means that this side of the coil wire is always attached to there, and the red side is always attached to this side, but they don't meet in the middle. There's a gap between them. What we can also see, these little grey boxes on the side, these are little bits that are connecting onto the split ring commutator. So as this device actually spins, what we're going to see is there's going to come a point where the little gap lines up there. Now that's brilliant because it means that it's not then going to just snag it. So it means it can keep turning, because what it does is it's always going to have the current flowing the same way from the battery, but the different half of the coil gets it. So if we've got current in a positive direction on the left first of all, so from positive to negative going into the paper, and it then spins, then what happens is the right of the coil then has this same direction, positive to negative going into the paper. So as it turns, it just allows the current to always flow into the paper, positive to negative, out of the paper is going to the opposite direction. Now this is where we can then use Fleming's left-hand rule to give us which side's going up, which side's going down, and therefore we know whether it's going in a clockwise or an anti-clockwise direction. The second device that we need to look at is an alternator. Now an alternator still involves a coil of wire, and it still involves it spinning between the poles of a magnet. What we see with our alternator though is that it's going to generate an alternating potential difference. So the reason for this is in the actual design. So when we're talking about a motor, we had that split ring commutator, so the two little semicircles with a gap between them. When we're talking about an alternator, we don't have those. Instead, we've got two devices called slip rings. Now, what we see is that on those slip rings, one is attached to the left-hand side and one is attached to the right-hand side of our coil. Then they rest against these little carbon brushes. They're not permanently attached, they just rest against them. So they're constantly in contact, but they're not physically attached to them. Now this means that as the coil of wire is spinning, then it's brushing against those brushes, and it means the circuit is always connected, but it doesn't tie the coil up in a big tangle. So what this actually means in terms of generating this alternating potential difference is we end up with a graph rather like this. So what we can see is that we've got the two sides to it. So we've got it going into the positive region and then into the negative region down here. So as that coil spins once, this is the graph we would see. So what's going to happen is it's going to be at one position, and then as it spins it's in the positive, and then it's going to start to decrease, hits this point where it's literally the 0, and then as it keeps going we drop into the negative region. So as it goes right the way around, we've got half in the positive, half in the negative. So we've generated this alternating potential difference. Our third and final device we're going to look at are dynamos. Now the dynamo is going to generate a direct or DC current. So what this means is that the potential difference that drives the current doesn't change direction. And the way it does it is by using our little split ring commutator again. Now what we see is a setup very similar to our motor. So we've got our coil of wire connected between the poles of a magnet onto those split ring commutators at the end. Now because of the way that's set up, as we said with our motors, then it means that on one side of the coil it's always going into the paper, for example, and the opposite side is always coming back out. So what we're seeing there is that the direction of our potential difference doesn't change. So we will generate a graph more like this, so it's always in the positive region. So what we will see is the direction doesn't change, so it's always going to be in the positive region, but we can change the magnitude. The last thing to really consider is how can we change the size of the effect in any of these devices. And there are two ways that overlap throughout all three devices that are really handy to remember. So the first one is we can increase the strength of the magnetic field, and the second one is we can increase the number of turns on the coil of wire, or the number of coils on that piece of wire. So those are two ways that you can do it that works for all three of those devices. If we're just looking at motors, then we can actually increase the speed of the motor by increasing the size of the current, by increasing the strength of the magnetic field, increasing the number of turns on the coil of wire, or increasing the length of the coil. So those work for just motors, and if we're then considering our alternators and our generators, then we could increase the strength of the magnetic field, we could increase the turns on the coil, or we can make it spin faster. So last thing to do then is let's have a look at some of the questions that they've asked over the years about these concepts. So what I'm going to do is I'll give you a chance to actually answer the question, and then we'll actually go through and see how to do it properly. Our first question is a multiple choice question. The diagram shows two poles of a magnet. X is the position of a wire carrying a current perpendicularly into the paper. Which direction does the current move? Pause the video to give yourself a chance to answer this question. So with this question then, what we need to do, Fleming's left-hand rule. So when we've got our piece of paper, remember your first finger here is going to point from north to south, so you can line that up nicely. And then it tells us that the current is going perpendicularly into the paper. So your second finger here is your current, and it needs to be this way round, so pointing in. Keep that first finger pointing north to south, and we'll see that your thumb is now pointing downwards. So the answer to that is A, which is downwards. Second question. Write down the name of the rule which can be used to predict the direction of the force perpendicular to a current carrying conductor in a magnetic field. Pause the video while you have a go answering it. So the answer to this one then is Fleming's left-hand rule. They will also give you the mark if you said just left-hand rule or motor rule. Our third question. A student places 4 wires of different lengths perpendicular to different magnetic fields with different currents flowing. Look at the table of their results. Use the data to show that wire D experiences the highest force. Show your working. Pause the video here to have a go at doing this question. So with this one, because it's actually asking us to show our working and it's a calculation question, then obviously we need to use some kind of a formula. The good news is it's one that's actually on that lovely formula sheet we get given. So what we're looking at is this one here. Force on a conductor is our magnetic flux density times the current times the length. So what we need to do is use this calculation. Now in the table, what we could hopefully see is that when we look at A, B, C and D's values, then D actually has the highest values for each. So we could actually start just by jotting down a sentence that says that D will have the highest force because it has the highest values for the magnetic flux density, the current and the length. Then we need to show with our working, because that second point there, show your working, is where we've actually got to do these calculations. So the first thing we need to do is obviously looking at our magnetic flux density, do our 0.10 times 2.5 times by 0.5. Get your calculator out, because your calculator is going to be immensely helpful when it comes to your physics exam. Then we just type those values in and we end up with our answer for A of 0.125. Now if you do that for each of the others, then we should end up with A as 0.125, B is going to be 0.225, C is also 0.225, and then D is 1.250. So we've shown our working, and what we should end up with then are all of your calculations written down like this, obviously A, B, C and D with all the answers there, so that you've then proven it, and that will get you your 2 marks. Next question is another multiple choice for us. So a wire is placed inside a horseshoe magnet. Which direction will the wire move when the switch is closed? Downwards, left, right or upwards? Pause the video here and have a go at answering the question. Okay, so on this one, again we're going back to Fleming's left-hand rule. The diagram though is a little bit trickier to interpret. So when we look at it, obviously we've got our north and our south, but over here we haven't actually got this labelled as positive, negative, and we've not got any arrows, so you've got to work that out for yourself. Hopefully remember that the longer line here represents the positive terminal. So what we're going to be doing is Fleming's left-hand rule. Remember, first finger, that is north to south. So we're going to start off by angling that, and that's pointing into the bit of paper. Then this current is going positive to negative, so we need to flip our hand round this way, and that means our thumb is pointing downwards, and therefore the correct answer is A. Next question we've got then is another multiple choice. So a 0.5 meter length of wire is placed inside 4 different magnetic fields. Which magnetic field has the greatest magnetic flux density? So pause the video and have a go at answering the question. So to solve this one, again we're looking at our formula sheet. So back to our physics equation sheet here and using this same formula. Okay, so force is magnetic flux times current times length. But we need to rearrange it. Okay, so in this case we're trying to work out our magnetic flux density. So that's got the symbol of B when we're doing this, and that is going to be rearranged to that. Okay, so force divided by the current times length. Now the good news on this, you don't have to work all these out, because when you look at our little table of our values here, we can see they're divided up into basically 2 groups. So if we look at the force on the wire, they've either got a force of 2 or a force of 4. Now it tells us up here that the wire is 0.5 meters, so the length is not going to change. All that's changing is the force and the current. So as we've said, using our little equation that's rearranged here, then it's going to be force divided by the current times length. So what we want to make sure of is we've got the largest force. So when we're looking at these, straight away we can cancel out A and B, because these have only got a force of 2, these have a force of 4. So it's going to be either C or D, and then if we're dividing that, then we want to be dividing by the smallest number to get the greatest flux density. So that leaves us with our 4 there and the 0.1 here, which means the answer is C. Next question. A student sets up an experiment to investigate the magnetic field around a current carrying wire. Describe how the student could use this experiment and a compass to investigate the magnetic field produced by the wire. Pause the video here and have a go at doing the question. So when we come to answer this, first thing we need to do is look at the diagram they've given us. So we've got the setup of the equipment there that shows us that we've got a piece of cardboard clamped into a clamp stand with the current carrying wire passing through it. Now it tells us that we've got to use a compass to investigate this, so make sure we are using the compass. It's worth 3 marks, so we need 3 distinct points here. So the first thing we're going to do is place the compass onto the card near the wire and then turn it on. So that's enough to get us our first mark, is talking about placing the compass onto the card or near the wire and then having that current turned on. Second mark comes from to observe the direction that the needle points. And our third mark is for saying that we're going to repeat this, moving the compass so it just moves to the next little section along and so on, and we plot it onto the card. So what we're really doing here is we're repeating at different distances. So when we look at the mark scheme, you got 1 mark for saying place the compass onto the card or near the wire. Second mark for plot or observe the direction of the compass or the needle. Third mark for repeating it sort of tip to tail or plotting it onto the card. And the final way you could get a mark is for repeating it at different distances from the centre. Final question then, draw the shape of the field which would be found around this wire. Pause the video and have a go. So to answer this one, we're going back to our right hand thumbs up. Because we've got a single piece of wire passing through the cardboard, we need our right hand with our thumb sticking up. Looking at the diagram that we had on our earlier question, then we can see that it's actually passing down into the piece of cardboard. So your thumb is pointing downwards. Now that gives us the direction is going to be clockwise. So when we then come to draw the shape of our field line, because it's a single piece of wire, it's obviously the circles. So we need something like this, and because it's going clockwise, then we need to add the little arrows going in a clockwise direction as well. So when we finished, we should have something like that to get us the mark. Now you've got to have 1 or more circles around the wire for the first mark, and the second is for your clockwise arrows. Don't forget to like, comment and subscribe on this video. Let me know in the comments if there's any topics you want to see in the future, and obviously subscribe so you know when the next one is posted up.